With question. I believe I still remember how these things go. So I'm going to be talking about active galactic nuclei. And what this is essentially is just accretion of material onto a black hole. Not the stellar mass black holes that we find normally distributed throughout a galaxy, but onto the supermassive black hole that are typically located at the center of galaxies. Now, accretion is really good at generating light. Optical light, radio light, X-ray light, light across the electromagnetic spectrum. So when you observe these things, what you often find is something bright or active in the nucleus or center of a galaxy, hence active galactic nuclei. Now, as I said, that they're detected throughout the electromagnetic spectrum. And you know how astronomers like to categorize things, like type 1, type 2?
I'm familiar with that.
Familiar. With AGN, there's about, what, 30 different classifications at this point in different optical classifications, X-ray one, infrared ones, radio ones, all of which are probably, so they're not one-to-one, they're not unique, but there's, and in, for example, the optical, what we really see is a continuum in properties. But in the radio, there actually seems to be a dichotomy. So if you look at a simple quantity, the luminosity at 1.5 gigahertz, and 1.5 gigahertz is not a special number. It just happens to be the frequency where most of the observations were done. And you divide it by the stellar mass of the galaxy, and you just plot what do you get for AGN. You don't get a power law like you do for pretty much all other properties of these systems. What you get is a bimodal distribution. So this is higher values, these are lower values. About 10% of the AGN are in this higher distribution. These are called radio loud. 90% are in this lower part, radio quiet.
Is that mass?
No, so the bottom, sorry, this is actually the number of galaxies. Down here is this quantity, sorry. But it turns out that these radio loud ones are almost always very massive elliptical galaxies.
Can I ask about like specifically where this is when you take an optical sample and ask what's it's doing in the radio, or this is I've taken a radio survey and
so if you did this with FIRST,
right,
where you just took all of the sources, tried to get rid of the ones which were star-forming galaxies, which fall on a 1.5 gigahertz H-alpha relation. So take the ones that have radioluminosities above that, divide by stellar mass, plot it, you get this distribution. Let's say you took an optical catalog of AGN, looked at which ones were detected in the radio, got their radioluminosities, divide by stellar mass, same distribution.
Okay.
So this dichotomy works for all types of samples. You have a radio sample, you see 90% radio quiet. Maybe the percentages change, but
right.
The fact that it's bimodal seems to be consistent for different, whether you look at optical AGN, whether you just look at radio surveys, you just see this difference.
how empty is the valley? You've drawn the valley as if it's exceedingly empty. Is it truly empty?
It's not truly empty. It's like Green Valley empty. So there are sources that fall in between them, but it's well described as the overlap between two Gaussians.
I see.
So, I mean, it's not that there are none, but there's a definite decrease in the number of sources in between the two.
What's the factor? Is it a factor of 5, 10 between the peaks?
It's about a factor of 10, maybe more. And that's one of the things that depends on which parent sample you use to do this, but it's much wider than the width. And it's about an order of magnitude difference in radioluminosity.
Since you're an astronomer, you didn't write a log in front of that, but you probably need log L 1.5.
Well,
That's a lot.
If I put numbers, then I would have to
Right, yeah.
give a log.
But conceptually, it looks like this when you take the log of that or
Yes.
use a log scale.
Other questions? Okay. So these radio loud ones are typically found in very massive galaxies. And since the most massive galaxies happen to be elliptical, these are often elliptical galaxies. And in fact, these are often the elliptical galaxies in the center of clusters. And the radio emission from these are jets. So a jet is a very collimated highly relativistic beam of particles. They originate on parsec scales. So you can observe these jets forming or emission from these jets from the central light years around the black hole. And they can extend, I think, for the most, maybe close to a megaparsec in the most extreme examples. So
You indicated the radio emissions from the jets, but they're these giant radio lobes that must be, they're so huge, they must.
right, so the jets are thought to, so
Create
they're
the loads.
collimated, and then once they lose the collimation, you have all of these relativistic particles that kind of fill the bubble within the ICM that's around these, and that produces the radio lobes.
But I'm just, you had said that the main emission was from the jets. and I just wondered if you were throwing in the lobes. 'cause
So,
I always thought
so-
the lobes-
I'm kind of, so most, normally when you have lobes in jets, the jets are brighter than the lobes. There are systems where the jets have turned off. But the cooling time of these particles is so long that you see the radio lobes. Those are often referred to as relic radio galaxies. But for the intents and purposes, they're essentially a product of these jets. So it's this jet emission that produces the radio lobes. They're a byproduct of it. So the radio loud ones, there's still a lot of discussion on what produces these jets, how you get this collimated material, how does it stay collimated for megaparsecs, but where the radio is coming from is kind of well understood. For these radio quiet, it's not well understood. And part of the problem is that they're quiet but not silent. So we do see radio emission from them, but it's a low luminosity. So,
And just, this is slightly off topic, but though the radio loud ones are very, by and large, very massive elliptical galaxies, the radio quiet ones, is it true that they're more diverse? Like there's a diversity of masses
Yes.
and types?
so the radio quiet ones, low mass galaxies, high mass galaxies,
Right, okay.
Seyferts, quasars, X-ray bright, X-ray faint. These radio quiet ones really fill every type of galaxy. So the radio loud, we think we know what's driving the radio emission. And we sort of know what type of galaxies form these. The radio quiet we see from a diversity of galaxies all over. So if you just look at the other classification schemes of galaxies and AGN, you just see them spread out all over. So that's sort of the question is what could be producing the radio emission in these galaxies? And since you have a diversity of galaxies and a low radio luminosity, you have a diversity of possible origins for the radio emission. So
I hate to keep interrupting you here, but what about completely radio silent? You just mentioned it. Are there a class of AGN that really don't seem to have radio at all
So-
at this level of sensitivity?
So it's the question of this level of sensitivity. There are AGN where you don't detect radio emission. But if you observe long enough, you would probably see something.
So you think it's just, those things would just be the left-hand
Yes.
tail of that?
Yeah. So what we're trying to do is what generates the radio emission from 90% of AGN. So this would be a good time to mention the other people who are actually doing a lot of the work on this. So this is being done by Abdullah Al-Husani, who is a researcher who initially started working with Jinzah, another professor at NYU Abu Dhabi, and we've been doing this with Ari Laor, and Sina Chen at the Technion. So here are the different collaborators on this project. And the way it got started was what generates the radio emission from 90% of the AGN. They wrote a nice article where they said, oh, it could be mini jets, the smaller versions of what you see from radio loud ones. It could be from the corona of an accretion disk. So if you look at the hard X-ray emission from AGN, in order to explain it, you need some very hot or relativistic plasma of electrons and positrons, Compton scattering the emission. If you have relativistic electrons and you have a magnetic field, you can generate radio emission. So it can be these. Another possibility is that maybe it's photoionized gas. AGN produce a lot of high energy radiation that ionizes the material around it. That's how they're identified. One of the ways they're identified in the optical. You have ionized gas. It emits thermal Bremsstrahlung in the radio. Photoionized gas. Jets, corona, photoionized gas. AGN can also trigger star formation in their surroundings. Stars form. Stars blow up. When stars blow up, they produce cosmic rays. Cosmic rays interact with the galactic magnetic field, also produce radio emission. The third one,
Is that third?
sorry, the fifth one, just so I can remember how to count, is AGN, or this, drive winds. Winds, if they're fast enough, can shock their surroundings. That produces cosmic rays. And that, so you have cosmic rays, you have a magnetic field, that can also generate the radio emission. So these are 5 completely plausible ways of generating radio emission in 90% of AGN. So the question is, which is it? Why would we like to answer that? All of these imply something different about the AGN feedback. So one reason why AGN are important is the impact they have on the evolution of their host galaxies. There's the radiative feedback that can heat up gas, preventing stars to form. There's outflows that they can drive, preventing gas to form. Kinetic feed, there's the kinetic feedback, radiative feedback, hot mode, cold mode. There's now lots of different terms about it. These different ways of producing the radio emission would be associated with different modes of AGN feedback. So part of the idea is if we can figure out which of these is going on in AGN, or try to understand in what types of AGN do you have radio emission from these processes, that might better understand how do AGN impact their hosts.
What's the width of the lower peak that you're trying to explain?
So
You
it's,
characterize
yeah,
it
yeah.
as narrow, but.
so it's about a factor
three.
of like 3, 4. So it's much narrower than the distribution between them. And
No,
they're
no, I
different.
was just interested in the absolute width, because that, some of those look harder to make it kind of quantized.
Exactly. And the thing is, it's not either or. One could imagine that in AGN, you have a combination of these things going on at different processes. All of these are physically plausible mechanisms that happen in systems. So is it a combination? Which one dominates? Which one dominates in what types of galaxies? Do you even expect to have any? Can you even expect to disentangle this at all?
Since you brought up the effects on galaxies, what about the Milky Way? So the Milky Way, as I understand it, is not an AGN.
It's not an AGN now.
Good, I was just gonna ask that. Do we know that it must have been an AGN in the past?
So there is evidence that there was an AGN in the past. Neil's not here. Okay. So do you believe that the Fermi excess is due to interesting forms of dark matter? Or do you believe that the Fermi excess is due to a population of relativistic particles left
Are you
behind?
thinking of the Fermi bubble?
I'm thinking of the Fermi
Right,
bubbles.
so nobody ever proposed that as
Okay.
dark matter, I don't think. But anyway.
Well, initially the Fermi bubble.
You're not talking about the excess at the galactic center.
So there's the Fermi bubbles seen in the gamma rays. And then there's also this,
The haze, right? The Fermi haze is
so there's the Fermi bubbles, and then there's the haze. And it's unclear to me if the haze is now distinct from the bubbles or not.
a little hazy.
It's a little hazy. And then there's also, so there's a lot of molecular material near the galactic center. And molecular material is good at reflecting X-rays, in particular iron K alpha, at the iron K alpha line. And there's evidence of molecular clouds kind of in the galactic center region, but further away, having had, so they're emitting iron K alpha now, but not ones closer by, which is interpreted as that there was a flash of some X-ray activity in the past that illuminated these clouds, and now we're seeing kind of like light echoes, but of past AGN activity.
I mean, it's also the case, I mean, if AGN feedback is important to the way disk galaxies evolve or grow, and we're a typical disk galaxy, then presumably there's a belief or a growing belief that there must have been AGN activity in the past because we've grown typically.
Yes.
But it's interesting to trace it all down. Anyway, I didn't know about the K alpha.
Is the timing of a K alpha reflection consistent with the timing of the size of the bubble?
It's all broadly consistent with sort of the million-year timescales.
That would be a good astro seminar, by the way, for us.
They do detect Sagittarius star in the radio. So Sagittarius star is very radio quiet, but it's not radio silent. So if you have all of these different mechanisms and you have all of these different galaxies, why would you possibly believe that you can draw some connection between these mechanisms and these different types of galaxies? So there was a study done by these two and a couple others where they looked at a sample, the PG galaxy sample. So these are optical quasars. Nearby, well-studied, lots of multi-wavelength information of them.
What does PG stand for?
Palomar.
Palomar green, yeah,
Oh, okay.
it was done by Green on the Palomar telescope.
Not a green filter. green person.
And
Green
not to be
person, yeah.
Confused by Green Valley or anything like that.
Yeah, not to be, yes,
It's very old, right? It's 80s, isn't it?
yes.
Maybe
Maybe
even earlier.
because the radio survey is from '84,
Oh, right.
because it was one of the first projects done by the VLA.
70s, maybe.
So these are very well studied galaxies, very bright. And which means is that people have measured what's called their Eddington ratio. What is the luminosity of the AGN divided by sort of the maximum luminosity you would expect given the mass of the black hole? The sample has also been observed in the radio by different people at different frequencies. So they looked at what's called the spectral index between 4.8 and 8.5 gigahertz. So what's a spectral index? You have flux density, you have frequency. You have 2 points. Since we're astronomers, we plot log flux density versus log frequency. Fit a line between them. The slope of that line, or the power law index, is the spectral index. And they found something interesting. What they found was at around an Eddington ratio of around 0.3, there was a change in the radio spectral index of these quasars. Below 0.3, you had typically flat spectrum. So this is a spectrum less than minus 0.3. And I'm using the convention flux density is proportional to frequency to the spectral index. These are steep. Alpha greater than minus 0.3. Now, what's the physics behind this? If it's a jet, the dominant radio emission is optically thin synchrotron emission. If you have optically thin synchrotron emission, the spectral index tells you something about the energy spectrum of the particles. In these sources, the particles are accelerated by Fermi acceleration. Typical spectral index is around minus 0.7, but the particle spectrum you can get out of Fermi acceleration changes. But in general, it's less than minus 0.3. Sorry.
You got your grader.
Yeah, I got my grader in less than. More negative, less negative. I apologize. So what that suggests is, depending on the Eddington ratio, there's a different, the origin of the radio emission is different. For higher Eddington, it's consistent with optically thin synchrotron emission. For lower Eddington, it's something else. Maybe it's optically thick synchrotron emission, maybe it's a different emission mechanism, but what's generating the radio depends on the Eddington ratio of the AGN. Now the
And that at AGN luminosity is like bolometric luminosity as best people can.
yes, so this
Because
bolometric,
I was thinking about how it connects to the fact that you're radio quiet. So like high Eddington, radio quiet,
so it's bolometric luminosity. And since these are PG quasars,
I see.
they have a very well measured broadband SED. So they estimated this from the broadband SED of the quasars. It's not, let's measure O3, estimate a bolometric AGN. These actually might be decent Eddington ratios.
So do these two blobs fit with the two bumps or not?
No, these are all
Oh, they're
radio
all-
quiet.
Okay. All radio.
That's
So
why I was
all of these are radio quiet.
I see.
I forgot to say that. So they just did these for radio quiet ones.
So for radio loud, the index would be consistent with -0.7.
So for radio loud, sometimes you see a flat spectrum core, but and then you see this -0.7 jets extending outwards. And the idea is that the base might be optically thick, flat spectrum. And then the jets are this optically thin synchrotron emission. And this is what you typically see from radio loud AGN. Now there's a whole subclassification of radio loud AGN, FR1, FR2. I don't want to go into that just because physics, not astronomy, zoology. There appears to be a physical difference between radio quiet and radio loud. And if this Eddington ratio tells us something about the physics of accretion onto the AGN, then this suggests that there might be some physics between the radio properties and the accretion physics. Make sense so far? But do you have a question or? Yeah, okay,
Thinking about it.
sorry, it's hard to,
Oh, right. With
with the math, I can't.
If I look puzzled, I was just trying to see if I could figure out which of these is going to be good candidates.
Literally, the example I give of what's different about being in an astronomy department versus a physics department is that in an astronomy department, people talk about FR1 and FR2 radio sources. That's literally the example I always give when people ask.
I have an astronomy PhD. I did come from a radio astronomy background, so I'm.
So I'm sorry, it might be a little insulting. but
No,
I-
no.
to you.
The field has progressed from FR1 and FR2. And that's just a geometric difference. Now, so anyway. So what we wanted to understand, why is there this connection? Why is there a connection between the radio spectral index and the Eddington ratio? This connection suggests that there's something different going on with the accretion onto the AGN. And that should manifest itself around the AGN. So what we did, and by we, Abdullah did a lot of this, was we did VLBI observations of 8 of these radio quiet PG quasars. Why did we choose 8? Because 8
Is
is,
that a Q or a G?
It's supposed to be a Q.
it is supposed to be.
Okay.
I apologize. Still jet lagged, Mr. Ryan. Yeah, radio quiet PG quasars. Why 8? Because that's the amount of VLBI time we had. We chose the 4 with the most positive spectral index, and we chose 4 with the most negative spectral index. So essentially we chose these 4 and those 4. They span actually a reasonably wide range in Eddington ratio, from 5% up to 100%. But the radio spectral indices is estimated from archival data, very positive, very negative. And we observed them simultaneously at 1.4 and 4.8 gigahertz. So what we have is a spectral index. If we detect parsec scale emission, we have a spectral index of that parsec scale emission. So
VLBI has parsec resolution at these distances.
So we did it with the VLBA. Our angular resolution is milliarcseconds, which translates to a few parsecs at these ranges. So if we detect something, we're detecting it within 5-10 parsecs of the center of the galaxy. And we can't detect anything bigger. Because this is an interferometer.
Yeah.
So it operates in Fourier space, not image space. And depending on where the questions go, we can go into that later. So what did we see? So we have 4 flat spectrum AGN, 4 speech spectrum AGN.
In contrast, what was the resolution of the PG galaxy survey? The angular-
So this data at, so this was compiled from different VLA observations at different dates, different configurations. The angular resolution ranged from 1 to maybe 30 arcseconds. So we're doing a factor, more than a factor of 100 better. So this was compiled, the total radio emission from the galaxy. The center, everything else, and it didn't have the angular resolution to distinguish between the two. It was essentially an unresolved blob. This is the total radio emission from the whole galaxy. This is the spectral index. That's what they could measure. Since this appears to be correlated with the property of the AGN, we thought, wait a minute. If this is real, there should be some correlation with the radio emission just coming from the AGN, not from the rest of the galaxy. If you look at these galaxies in the optical, all you see is the quasar. But there is star formation happening in these galaxies that will produce radio emission. You can't distinguish it based on these observations. You can do it here.
How do you get the Eddington luminosity? Not the volumetric luminosity. How do you get the denominator of that?
So there's these atlas of quasar SEDs. So one, Hubble did observe these and was able to get some information on the
Like
host. So
The
you
mass
can,
of the bulge or
the
something.
mass of the bulge, so you can get something about. There's also these quasar SED fitting where the multi-wavelength shapes depends on Eddington.
So, okay.
So we shouldn't 100% believe the denominator. In fact, the strongest argument that the denominator is actually okay is that you see a break.
So I wouldn't necessarily believe this 0.3.
Right. You're probably
There's
right.
almost certainly systematic errors in here, just how you estimate this Eddington ratio. But it was all done consistently, and this is what's important. So they used one method to get the Eddington ratio of all these quasars. The higher ones really had steep radio spectra. The lower ones had higher radio spectra. This value of 0.3, there's uncertainty there just because there are different ways of estimating that ratio. So we observed them with the VLBA. What did we find? First, what did we detect? When you have a jump in 100 angular resolution, what might appear compact and very bright at poor resolution is completely undetectable at high resolution. So what we found is that of these 4 flat spectrum galaxies, we detected 3 of them at both bands. That actually tells us something already, that the emission is very, very compact. The angular resolution is lambda over d, where lambda is the observing wavelength, d is the distance between antennae. Observations happened at the same time. This is fixed. 1.4 and 4.8 gigahertz, this is 20 centimeters. And this is 6 centimeters. That difference in 3 actually leads to a difference in 3 in the angular resolution. So it's possible that something would be small enough to be seen at 1.4 gigahertz, but too big to be seen at 4.8 gigahertz. That wasn't the case for any of the detections of the flat spectrum one. For the steep spectrum ones, 2 of them were detected, but only at L band. Of those, one has sort of 3 sigma C band emission.
Do you mind reminding us which one is L, which one is C?
Sorry, 1.4. I did radio astronomy background. Believe it or not, those letters are a holdover from World War II, where they chose the frequencies and gave them letters to confuse whoever else might be listening to them.
And then we kept them as. a
And then we'll
useful
talk.
It's a fond memory.
It's astronomy.
Yeah.
Well, it's the same people doing one and then the other. So they
Can't figure it
Can
out.
I ask one more question?
Yeah.
What's the field of view? Because if you have to aim for this thing, which is 100 times smaller,
Yeah.
like,
So the
do you
field
map the
of,
whole galaxy? Or?
so the field of view is a few arc seconds. So we know that the center, we know the position of the center of these galaxies to much better than this. So the nucleus is in the field of view. Most of these were detected near the center, but not exactly at the center, which is a good sign.
Yeah.
Because we don't know the center 2 milliarc second.
And you're not showing us images because the images, well, because it's
not allowed
Brown
to.
Bag, he's not allowed to. And second of all, were the images like interesting, or is it basically you just see one source?
So for the flat spectrum sources, they were unresolved in the images. You imaged it, you got a single blob. If you fit it with a Gaussian, the routine would return some extent. But they were unresolved.
And consistent with the astrometric center of the quasar.
They were less than an arc second. They were like 0.1 arc second away from the center of the galaxy. Yeah, and there were no other sources. Yeah.
Good.
For this one of them was unresolved at 1.4. Nothing at 4.8. The other one, so first we have just a difference in the detection statistics, small number of statistics, but 3 out of the 4 were strong detections in both bands. 2 out of the 4 we detected at one band, but only one was very weakly detected at the other band. The one that was weak, so the one that wasn't detected at this other band we saw was, it's not actually unresolved. It's one component, but it's more, so it's semi-resolved. The other one,
So does that mean detected or not?
no, so it was detected
Yes.
and we have some extent,
Oh, I
but we
see.
don't see internal structure.
I see.
So it's not like there's
One
a
source.
point and say a narrow feature coming out. The other one looked like this. So I had 2 components. And so once we had the position, once we had this image at 1.4 gigahertz, we can look at the higher frequency one and ask, do you see anything? Because now we know the position of the emission that we're looking for. For this one, there was just nothing. at 4.8 gigahertz. Here, we detected faint 4.8 gigahertz. This one was brighter. So we detected 4.8 gigahertz at both. But the distribution, so at 1.4 gigahertz, so this one was brighter at 1.4. And these are relatively brighter. So I'm not talking about raw millijanskis. I'm just saying the fraction of the emission, this one really dominated at 1.4 gigahertz. This one was close to half it. So at 1.4 gigahertz, it's like 2/3, 1/3. At 4.8 gigahertz, it's closer to 50-50, which suggests that this has a flatter radio spectrum. And this has a steeper one. And this is true even if we take into account the different UV coverage, blah, 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 blah. I can get into the technical stuff on that, but if people want. There was also, the other thing is, okay, we measure total flux as a parsec scale. How does that compare to what was the total emission from the galaxy measured before? For these flat spectrum ones, so the parsec scale was 50% to 90% of the total galaxy. So the central 30 light years, 10 parsecs of this galaxy was really producing the bulk of the radio emission seen from the whole thing. For these, at 4.8 gigahertz, the higher frequency. From these, from the two detections, it was about 10 to 25%. Of the total galaxy emission at 4.8 gigahertz. Now, you can ask, well, what about the upper limits? So there's some we didn't detect. Should we have detected them if they had compact radio emission? And our upper limits are at this 10% level. So the fact that we didn't see them suggests that less than 10% of their emission is coming from a structure smaller enough that we can see. Okay. The other thing we can measure is, well, we did these two frequencies. We can measure a spectral index between them. And in fact, these flat spectrum ones are flat at parsec scale. And our detections are steeper at parsec scale. So what we do see is, so we are seeing some physical differences between these two samples. And when we measure their properties on parsec scale, there's sort of what you would expect that this correlation is due to sort of the physics around the black hole. So I have 15 minutes left.
Yeah, or 13.
Okay, no, good. So these are the basic results. So now what do we think is going on? Now, you asked, so one is a brown bag, no images. The images are not necessarily that insightful, but we are able to measure the sizes of the radio emission. And what we found is, so we have low Eddington, high Eddington. Low Eddington sources. But we can talk about the parsec scale emission of these. Parsec scale is a significant fraction of the total galaxy. Here it's smaller. At 4.8 gigahertz. The reason why I keep on saying 4.8 gigahertz is at 1.4 gigahertz, if you add these two components together, you actually get a high fraction of the total of the galaxy. Here at 1.4 gigahertz, you also get a high fraction. So it's actually a similar fraction. The difference is for this galaxy, it's those two components. It is coming from something that's large on parsec scale, much smaller than the galaxy, but we clearly see these two differences. Here, it's point like at 1.4 gigahertz. So the physical size of this is on the order of parsecs. This other detection was also somewhat resolved. This size is on tens of parsecs. Here we can kind of put upper limits on the size of like 5 parsecs. For those two detections, it's like 30 parsecs, 50 parsecs big. Flat spectrum. Steep spectrum. So these are kind of the pieces of information on what we see is going on. So the question is, can we try to come up with a model that explains why these properties would change with Eddington ratio? And so, for example, this size, we have a galaxy at like 5%, a couple at 30%, 80%, and 100%. And the size actually, okay, we're talking about 5 data points, but it does increase. So it's not necessarily the sharp transition we see here, but we do see trends with our small number statistics. And we are working on expanding the sample. We just haven't analyzed the observations yet. So what do we think is going on? We have a black hole, and we have a disk of material around the black hole. You have a disk, it's hot, it's ionized, it's moving around, you're going to generate a magnetic field, you're going to have a corona. And actually, I kind of lied a bit to your question on the image. One thing you can do about interferometers is by changing how you weight the data between different telescopes, you can change your angular resolution. And you can actually change it by a factor of 2 or so. So we have data. You just re-image it using different settings. What do you find? For these sources, you re-image it with different settings, they go away. What that tells you is that the source is actually big. You increase the resolution too much, you lose the emission. For these, the emission decreased somewhat. So the one's Eddington ratio at around 30% or so. The emission went down, which suggests, oh, they have a parsec thing, but they have something more extended. Now we had one galaxy at 10% Eddington. When we looked at it, it was extremely compact at 1 weighting, so we did higher weighting. And what we found are 2 very, very unresolved point sources about a parsec apart from each other that constitute all of the emission that we see. So that actually Abdullah just kept on changing the weighting until he got no detection, and then he found this. So definitely kudos to him on that part, because I was like, ah, you'll never find anything if you use robust at this setting. He's like, yeah, I'll just try it, and he did. So, and these two little blobs of parsec apart for this galaxy is 100% of what you see at 4.8 gigahertz. At 1.4, you'd never get the resolution needed to do this. But so the idea is that if you just have a disk, you're going to have a corona. And this is kind of supported by the hard X-ray emission. This radio emission, the radio emission from the corona is going to be flat spectrum.
Corona is defined as some diffuse, ionized, very hot gas. What is the
So-
definition of it?
It's hot ionized gas.
It's not in a disk, it's more like spherically distributed.
So it's above or below the disk. It's, so the reason why so it's optically thin at some wavelengths, it's optically thick at others. So this is why I don't want to say diffuse. The size scale is supposed to be of order, so like tens, maybe 1,000 RG. So this plasma is supposed to be very tight. You only find it, or it's confined to very near the center of the accretion disk. So much smaller than we can even probe. So for VLBI, this would be unresolved. And it's flat, possibly because it's optically thick at radio wavelengths. So the idea is that at low Eddington, you still have this corona, and this is where the radio emission comes from. As the Eddington ratio increases, something else happens. What you start to get is larger, steeper spectrum radio emission. By larger, I mean tens of parsecs. So we're not talking, so just VLBI, we can't see kiloparsecs, but much bigger than the unresolved point sources that the flat spectrum cores we're seeing in these objects. The steep, so when I say steeper spectrum, what spectral index do I need? And what we actually observe are spectral indices around -0.7. -0.5, -0.7, -0.8. This is optic, so this is consistent with optically thin synchrotron emission from shock-heated particles. So as the Eddington ratio increases, you start to generate a shock propagating into the environment, contributing the radio emission. And as the Eddington ratio goes up and up and up, this component begins to dominate. We observe this component getting larger or further from the center, and the total flux, or the relative flux of this steeper spectrum to flat spectrum, increases with Eddington ratio. So as the Eddington ratio goes up, it can start to generate these shocks, and they get stronger as Eddington ratio increases for these radio quiet AGN. Now the question is, what is generating these shocks? Is it, so one possibility is maybe it's a coronal mass ejection. The sun has a corona, turbulent magnetic field, you get mass ejections, those drive shocks into the solar system. Another example of this, this is going. are magnetar giant flares. Where, sorry, that this was half of my PhD thesis. So it was kind of a very back where a magnetar had this giant flare of gamma rays. Actually, Christmas was like 2 days after Christmas, which really hurt the radio follow-up because no one was working when it happened. But it was observed to produce a radio nebula. This magnetic event produced a shock in the surroundings, possibly the ejection of a magnetic flux loop that, as it expanded in the surroundings, shocked emission. Another possibility is, well, if Eddington ratio is increasing, you're getting more radiation. And you might be getting a radiatively driven wind. If the wind is going fast enough, that will shock the surroundings, producing radio. Now, to go back to the connection to AGN feedback, what this suggests is that the mechanism of the AGN feedback depends on Eddington ratio, whatever this explanation is. Lower Eddington AGN affect their environments differently than higher Eddington AGN. We don't see evidence of these shocks in lower Eddington. So whatever impact it has might be more the photoionization, the optical emission, the UV emission. These are all quasars. So they emit a lot of light at other wavebands. They're radio faint, but there is a high luminosity, a high bulk luminosity. As the Eddington goes up, we see evidence of these shocks, which suggests some kinetic power being injected into the environment, regardless of which mechanism that is. So that's kind of where we are. We're still trying to work on this picture. So the observations are done. We're working, Abdullah is working hard on a paper reporting these results. He's actually going to be giving a talk on this at AAS. So if you're going to the AAS meeting and you're interested, drop by, say hi. He can actually show you the images. I hope I didn't butcher his work too much.
Let me get a sign. Oh,
Oh, it's nice.
without Eddington getting bigger or smaller, because if, according to your, for fixing the relative importance, as Eddington gets bigger, you'll move to the left.
Thinking with Eddington ratio.
Eddington ratio. Sorry, I meant the Eddington ratio. You move to the right.
So this thing is the ratio, like L over L Eddington is what you call the ratio, right?
Yeah.
So here you mean Eddington ratio,
Eddington ratio, yes.
L over L Eddington.
So high Eddington.
So high
sometimes people
Eddington
talk
means
about
close
the
to
Eddington
Eddington.
ratio.
Yeah.
And being, it's a fraction between 0
Yes.
and 1.
Yep.
Usually,
Yes.
it could in principle get bigger. And so when you say LAGN over L Eddington, is that what?
This
you
is the
mean by
Eddington ratio. This is also between 0 and 1.
Yes, okay, and so when that is on the right, you should be getting the steep spectrum according to your picture.
Yes. And that
It's
is,
a high Eddington ratio.
yes, and that is what we see at parsec scales. Is that at higher Eddington.
Because the corona was the flat spectrum.
So what we see is that for lower Eddington ratios, we have just flat spectrum. All the radio emission from the galaxy is flat spectrum from a few parsecs around the AGN. We think that's the corona. As you increase the Eddington ratio, the corona doesn't necessarily go away. So in fact, we can play with the data to try and get even better resolution, calculate spectral indices, and what we find is that if we look on more and more compact scales, the spectral index gets flatter. I could give electron interferometry, but I won't. So we believe that the corona is still there, but its relative contribution to the total we see is smaller. Most of the emission is diffuse, not 2 parsecs, 20 parsecs. and it's deep spectrum. And it kind of monotonically increases small samples, very small samples, as the Eddington ratio increases.
I mean, of these things, like that could be 1, 3, 4, 5.
So we're not, so what we think is going on is that for the flat spectrum, it's probably 2.
Right, yeah.
Yeah. For the steeper spectrum, it's probably not 3 because photoionized gas would be thermal Bremsstrahlung. Thermal Bremsstrahlung has a spectral index of around 0, inconsistent with what we're seeing.
I see.
It's probably not 4 because the star formation triggered by AGN would be on size scales bigger than 20 parsecs. If you had a nuclear star, but
Because,
well, so even if the stars are only within 20 parsecs, they blow up, they produce cosmic rays. It would be very difficult because we're not seeing radio emission from the stars.
right,
We're seeing radio emission from the cosmic rays accelerated in the supernova and the chocks as it expands into the ISM. You would need a very strong central magnetic field to keep 1 million years worth of cosmic rays bottled up in 20 parsecs.
Alright.
Because if it's any bigger, we don't see anything at the VLBA.
Yeah, although you do have room for there being like substantial unresolved.
Yes,
emission.
so that's one of the things that we're also beginning to investigate is for these galaxies where we don't see the VLBA emission, what is causing that?
Mhm.
Is it star formation in the rest of the galaxy? Is it, let's say you generate this wind for 1 million years, or sporadic, or you have CMEs just ejected sporadically over 1 million years. Is the remainder, the diffuse emission, just a sum of previous AGN injection with time, or is it due to star formation or things like that? So those are all, we can't answer that yet. But what really surprised us was, we just said, we had VLBA time. We had to use it. We had talked about this project. This was at the beginning of the pandemic. And I was like, okay, let's pick sources. 4 flattest, 4 steepest. Submit the VLBA observation. Let's just see what happens. The fact that we got a really clear separation in the parsec scale properties was a surprise to us. And what we think is a physically interesting surprise, in that it actually relates to the physics, not astronomy nomenclature and things like that. This is not FR1, FR2. Going back here, for the parsec scale emission, we don't think it's 3 or 4. It could be 1, and it could be 5. Now the question is, what do you mean by a jet? For these radio,
Sorry,
huh?
I thought you told us that corona was responsible for the parsec scale.
Oh, for the flat spectrum parsec.
So you're talking about like the 10 parsec scale now.
So yeah, exactly. So this is sort of like less than 10 parsecs. Now there's the stuff we see on
Now you're
tens
moving
of
to the slightly
parsecs.
higher. Okay, good.
Exactly. So for the lowest Eddington ratio AGN, all we see is the corona. And it's within 10 parsecs. As the Eddington ratio increases, we start to see emission on tens of parsecs. Can't be from the corona because one, it's too big, but it also has the wrong spectral index. It's probably optically thin synchrotron emission from shocked heated particles. What's generating the shocks? Is it a wind? Is it a jet? This has to do with the launching mechanism.
Is there a difference between a wind and a jet?
So are you asking Roger Blanford or not? Oh, and this is, so I think I should, well, the reason why is for these radio loud jets, they're thought to be launched by something called the Blanford-Zinaik mechanism, where they're generating, the energy is coming from the magnetic field is up very close to the AGN.
Yeah, right.
And that actually might be why they're only in very massive galaxies.
I see.
Only if you have the most massive, supermassive black holes, do you have enough energy to launch these jets? So one of the follow-up things we're doing, because this is small statistics, is there's manga. I have this manga project to study kiloparsec scale outflows seen in the ionized gas. The speed of these outflows, now, I don't know how to do the optical data. As you said in the beginning, I'm a radio astronomer. If you look at the speed of these outflows, they're thousands of kilometers per second. So as they propagate through their galaxy, they're probably driving shocks of thousands of kilometers per second. That should shock heat electrons to cosmic rays. That should lead to radio emission. So I had this JVLA project. Why don't I just observe with the VLA a whole bunch of outflow galaxies detected by FIRST? So we know there's radio emission, figure out where the radio emission is coming from. And I had this very naive idea, oh wait, the radio emission would probably, we can map out the optical outflow with manga.
Exactly.
We
We
can
can see nice like shocks in there, yeah.
Yep,
Beautiful idea.
beautiful idea. And it was great because it worked in one galaxy. And actually I had another student, Aisha Al-Yazidi, write it up, it was an FJ, where we saw this like nice radio structure, and then you map out the ionized gas outflow with manga, and there was some archival GMOS data we looked at, and it matches beautifully. For a lot of the other ones, we had, the radio emission was pretty compact,
Yeah, just a dot.
just a dot. For some of them, the manga outflow is also kind of dot-ish. So it might be that they're correlated just on smaller scales. For others, the optical outflow is more extended, so there's, but we observed a bunch of these with the VLBA as well, because we know they're radio AGN, they're radio bright, and we also,
Yeah, so now you can ask the same question on smaller scales if you can get the sensitivity.
but our results on these 8 PG galaxies seems to, so we observed like 20 of these with VLBA as well. And these results on 8 seem to be holding with this larger sample. So there might actually be something to it.
How hard, how expensive is the LPA timer? How hard is it to get? Is it very hard to get?
So the time we've used was bought.
You purchased it.
We purchased it. NYU
Interesting. So you
purchased it.
can't-
I'm gonna pause the recording. I'm not gonna pause it, I'm gonna stop it.
Okay.
Yes,
Actually,
I'm-
your student, Yosi, that's so nice and so interesting. I have a bunch of
Oh,
questions